Last class we discussed the conductance. Today we can discuss the various factors affecting conductance. First one is the nature of the electrolyte added. Second one is the size of the ions produced and their solvation. As the size of the ion increases, the conductance decreases. And the solvation means dissolution. When an electrolyte dissolves, what happens? It will dissociate into ions. As the number of ions increases, the conductance increases. The nature of the solvent and its viscosity. In the case of aqueous solution, they are good conductors as aqueous solution of electrolyte. The reason water is polar solvent. And temperature. As the temperature increases, conductance increases because more number of ions will be produced. Nature of the electrolyte, there are two types of electrolytes, strong electrolytes and weak electrolytes. Strong electrolytes are better conductors than weak electrolytes because of the increased number of ions in strong electrolytes. If we analyze all these five factors, we can conclude it into two, or we can summarize it into two: number of ions in the solution and speed of movement of ions. Number of ions in the solution and speed of movement of ions. As the number of ions increases, the conductance increases. Similarly, as the speed of movement of ions increases, the conductance increases. That will be clear from this picture. You see this picture. So in this picture, here the luggage is very big, heavy luggage. He is struggling to carry it. So in this way, if he want to cover 1 kilometer, he will take hours. But here you see the total luggage that is equivalent to this one. But they are not struggling. They are walking freely. So here what is the problem? Here the number of ions more, number of carriers more, number of charge carriers more. Here the number is less. So this one is struggling. But here more numbers. So they can easily carry the charge. Again, you can see he's struggling to walk, but they are walking freely. Here speed of movement is more. Similarly, more number of people are there. Therefore, they can carry the luggage easily. So here, because of the two reasons, more number and more speed, this one is a better, this one represents a better conductor. Now we can analyze what is the variation of conductance with the dilution. First, we can see the case of specific conductance. What is the definition of specific conductance? Specific conductance is defined as the conductance of unit volume of electrolyte or 1 ml of electrolyte. Whatever may be the concentration, it is the conductance of 1 ml. And you know, if you take a solution of particular concentration, 1 ml of a solution of particular concentration, that 1 ml contains a particular number of ions. As the dilution increases, the number of ions in this 1 ml that will decrease. Number of ions per unit volume decreases. Conductance directly proportional to number of ions. If number of ions per unit volume decreases, what is happening to the conductance? Specific conductance decreases with increase in dilution. Specific conductance decreases with increase in dilution. What is the variation of specific conductance with the dilution? Specific conductance decreases with increase in dilution. What is the reason for that? Because number of ions per unit volume decreases. Number of ions per unit volume decreases. That is the reason. Then what is the variation of molar conductance? You know, molar conductance is the conductance of all the ions produced by 1 mole of an electrolyte in a given solution. All the ions produced by 1 mole. So the number of ions, we are not counting number of ions in 1 ml or in 2 ml or in 3 ml. We are considering number of ions of 1 mole. We will consider that much volume. The volume that contains 1 mole of the electrolyte. So it is the number of ions present in a volume which contains 1 mole of electrolyte. So generally we can say molar conductance increases with increase in dilution. Molar conductance increases with increase in dilution. Here we have to analyze 2 cases. The first one is the case of weak electrolyte and the second one is the case of strong electrolyte. In the case of weak electrolyte, what is the definition of weak electrolyte? Electrolytes which are partially dissociated. Electrolytes which are partially dissociated in solution. They are not completely dissociated, only partially. As the dilution increases, what is happening? More number of electrolyte molecules will undergo ionization. As a result, number of ions increases with increase in dilution. If there is an increase in number of ions, what happens? Molar conductance increases. So in the case of weak electrolyte, molar conductance increases with increase in dilution. What is the reason? Number of ions increases with increase in dilution. That is the reason. And in the case of strong electrolyte, what is the definition of strong electrolyte? Strong electrolytes are completely dissociated even in concentrated solution. That is completely dissociated. So can you expect an increase in number of ions with increase in dilution? No, that is not possible. The number of ions are not changing. Then what is changing? Okay, the second case, that is speed of movement of ions. When the positive and negative ions are very close to each other, they will feel high resistance for the movement because of the attractive force. And as the dilution increases, the distance between positive and negative ions increases. Therefore, the resistance due to attractive forces will decrease and they will get more freedom of movement. As a result, the speed of movement of ions increases. Therefore, the conductance increases with increase in dilution. So in the case of strong electrolyte, molar conductance increases with increase in dilution. What is the reason? Reason, speed of movement of ions increases with increase in dilution because of decrease in attractive interactions between positive and negative ions. So here molar conductance increases with increase in dilution and finally it will approach a limiting value. It cannot increase to infinity. It will increase and finally attain a maximum value. Beyond that increase, beyond that limit, further increase is not possible. And that limiting value of molar conductance known as molar conductance at infinite dilution or limiting molar conductance or limiting molar conductivity. Molar conductance at infinite dilution is the maximum value that can be attained. So molar conductance at infinite dilution, that is the limiting value of molar conductance of an electrolyte. That is the maximum value that can be attained. If we plot the molar conductance against square root of concentration, we'll get a straight line graph for strong electrolyte and a curved graph for weak electrolyte. Here molar conductance plotted against a square root of concentration or C raised to half It is plotted against square root of concentration because the molar conductance of strong electrolyte is proportional to square root of concentration. We will get it from an equation known as Debye-Huckel-Onsager equation. A shortened form of Debye-Huckel-Onsager equation is shown here. You can see lambda m is equal to lambda m0 minus A0 raised to half. Lambda m molar conductance at the given concentration, lambda m0 molar conductance at infinite dilution. A is a constant into C raised to half, square root of constant. So here lambda m0 is a constant. It is in the form y is equal to mx plus c, equation for straight line. So if we plot the lambda m against c raised to half, you will get a straight line. So this is obeyed only by the strong electrolyte, but in the case of weak electrolyte, you are not getting a straight line, you are getting only a curved graph. So the graph will help you to find out the molar conductance at infinite dilution of strong electrolyte. But the molar conductance at infinite dilution of weak electrolyte cannot be determined from the graph because we cannot extrapolate the graph to y-axis. That means zero concentration. But in the case of strong electrolyte, we can extrapolate the graph to y-axis, zero concentration. So in order to find out the molar conductance at infinite dilution of weak electrolyte, we need some other method, or we need the help of some rules or law. So here we can see another law, Kohlrausch's law of independent migration of ions. Kohlrausch's law of independent migration of ions. In this law, what are the conditions? The condition infinite dilution. At infinite dilution, when the dissociation is complete, all the molecules of the electrolytes are dissociated completely. When the dissociation is complete. At infinite dilution, when the dissociation is complete, the law states that the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. When at infinite dilution, and the dissociation is complete. So what is Kohlrausch's law of independent migration of ions? At infinite dilution, when the dissociation is complete, the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anions and cations of the electrolyte. For example, you consider the electrolyte NaCl. Lambda 0 m of NaCl, molar conductance at infinite dilution of NaCl, can be represented as lambda 0 m of Na plus lambda 0 m of Cl minus. Lambda 0 m of NaCl plus lambda 0 m of NaCl is equal to lambda 0 m of Na plus lambda 0 m of Cl minus. We can express the molar conductance at infinite dilution of an electrolyte as the sum of molar conductance of individual anions and cations. That is Kohlrausch's law of independent migration of ions. So at infinite dilution, the ions are independent. At infinite dilution, the ions are independent. We can generalize this equation. During dissociation of an electrolyte, suppose gamma plus positive ions and gamma minus negative ions are produced. During the dissociation of electrolyte, suppose gamma plus positive ions and gamma minus negative ions are produced. Then lambda m0 of electrolyte is equal to gamma plus into lambda 0 of positive ion plus gamma minus into lambda 0 of negative ions. Where gamma represent the number of gamma plus represent number of positive ions and gamma minus represent number of negative ions. So I think we can stop it here and we can discuss the problems in the next class. Okay.